I'm also the VHDL Working Group Chair. So if you've got great ideas and you've been inspired by some of these other methodologies and you think we ought to be spinning it into VHDL, yeah, we can take a look at that. So we're going to be talking basically about the whole OSVVM parts here, parts and pieces of everything. What is OSVVM? It's a free open source library. It works with any VHDL 2008 simulator, GHDL, Mentor, ALDEC, work in progress, Cadence, and Synopsys. So we're getting noticed out there, and I think I'm really excited because Mentor Graphics is this year in their verification survey has included OSVVM and such, and I've seen the early numbers. I'm not allowed to talk about them yet, but they're good. They're much better than they were predicting in the past anyway. We rival other verification languages, except it's simple. It's simple, and we can use it for simple FPGAs. It's also powerful enough to use for ASICs. Works in any VHDL test bench, and this is what basically SystemVerilog is struck out on. It's similar enough to RTL that RTL designers can, and you can switch back and forth. Okay. It's intended to be readable by all. Okay, so, and by that I don't just mean verification engineers, I mean hardware engineers, software engineers, because if you don't have that, how do you do review, right? You limit the set of people who can review your test bench, then you go into the lab and you debug more. That's not fun. I don't want to do that. Okay, and so many people have included OSVVM as part of their methodology. If you look at UVVM, they get their randomization and functional coverage from OSVVM. But OSVVM by itself has, okay, so UVVM is just total overlap. Okay, so if you look at our test bench framework, we're basically the same as any other language out there that does test bench frameworks. We surround our designs with models, okay? We have a central place. Now this is different than what SystemVerilog does. We have a central sequencer that kind of drives everything, okay? From there, every test is a separate architecture of this one test control entity. Okay. That means our architecture, so we'll have one architecture that looks something like this for each one. At the present, we have a control process, but then we have one process for every different stream of stimulus. Okay, these are all talking to our models. They talk to our models via transaction-based procedures. I was calling the old stuff CPU write, UART send, but I'm stopping to doing things device specific, so I'm looking more to go to send and get for the transmit type interfaces and master read and write for the bus type interfaces. We have, since we're running which is different than some of the other methodologies. Some of the other methodologies want to do dispatch, which I think is going to make your head spin as soon as you layer randomization on top of that. So instead, what we've done is a family of synchronization primitives to allow the processes to pause until the other gets to this point under some conditions. The barrier is just like in software, all the processes are waiting until they get there. So it's like a join in a way, okay? We don't have fork in VHDL. I don't think we ever will because we don't really have any. We start concurrent and we program concurrent, okay? And we use the same sort of test bench framework, whether the models are entities architectures, that's my preference, but the models could also be a subprogram implementation in a package if you like. Okay. And all OSVVM capabilities work within this framework, or most of them work in any other VHDL framework. Okay. So basically what we have then is the way we communicate with our models is through records. Okay, and we've kind of abused records by layering in resolution functions that just say, ignore the fact that there's multiple drivers here. We basically, in most of the resolution functions other than standard logic, we basically use type tick left. as the ignore value, as the non-driving value, and then anything that's not typed to left, the maximum of that gets picked. Okay, and that's in another resolution package within OSVVM. But coming 2018, we really hoped it was 2017. We've had a lot of problems with frame. So it's looking at this point like it's going to be 2019. The language is adding a lightweight sort of interfaces, which is basically just a record that you can set your IO modes for. So you no longer have to have the record on the interface as in-out, which is what made us really mess around with resolution functions, which is, it's ugly, but it works. Okay. Then we get into some of the utilities, and one of the utilities in OSVVM is randomization. I was looking for, how do we do constrained random in VHDL? Okay? And the first question is why? Okay, well, if we look at a FIFO test, and the top is an analog display of the number of words currently in the FIFO, and we do a directed test of it, we can fill it, we can empty it, we can run it for a while. That low number in the middle is like 2 words in the FIFO. And then we can do some empty tests. We have some counters over there verifying that we really are trying to do reads while empties and we're holding them off. And then we fill it up. We can look at our test plan and check off all the little boxes and say, hey, we did it, right? But if you add randomization to that, you can really walk the space in a much better manner. So this is the why constrained random. This is why SystemVerilog went in the direction they did, because I can more convincingly not only check off the little boxes, but prove that my design really does what I say it did. Okay, and with a greater degree of confidence, I would say. So the key benefit of randomization is we can generate stimulus in a timely fashion. That's not execution speed, that's writing speed. Okay, and it's ideal when you have a large number of similar things to do. Modes, sequences, processor instructions, network packets, that sort of thing. That's the niche of constrained random, okay? But if the test is not faster to write or more thorough, then you ought to. Okay, so this is totally different from SystemVerilog because they basically buried their transaction initiation into the randomization. So they did a little too much abstraction, and you lose the illumination and you lose the ability to independently start them and do directed. Okay, yeah, you can do it, but you got to throw down constraints still, and that's crazy. Okay, so we have a very basic set of randomization in OSVVM. We can randomize ranges with an exclude, that's what's highlighted there. We use integer vectors liberally. And integer vectors allows us to express sets. They're on constrained arrays, so we can have any number of them. Okay. Sets with excludes. Weighted distributions. Weighted distributions are cool because we're going to use this in our sequencing, picking different weights of operations to do, for example. So the weights don't mean anything by themselves. It's the weight and the sum of the weights that means something. So we have a sum of 10. 7 out of 10 means we're going to do it roughly 70% of the time. It is a uniform distribution. That means we don't hit it real quick all the time. That means it's not balanced until you do thousands. But we can set a value and a weight, and that's nifty in some cases, but it's not as useful. Behind the scenes, there's a protected type. We needed a protected type in randomization because we needed the seeds as state. Somebody else was mentioning VHDL doesn't do functions with side effects or in-outs. Okay, and that's the reason for using a protected type, because we hide the state inside the protected type. Okay, so all that was just randomization. That's fine and dandy, but that doesn't get us to constrained random. How do we get to constrained random? And that's basically code plus randomization method. So we need patterns, right? We need patterns to do. So here's one. We'll use that dist-int 70-20 or 70-10-10-5-5 to do something. And maybe we're testing a UART here, and the first case says, yeah, we'll nominally do 70%. And I should add that basically the case indices come out to be 0, 1, 2, 3, 4, 5. In that order, they basically pick the index of the array, and when you just pass in a literal value, it works out to be 0 as the first one. So And then we can assign the next one to be inject parity error, the next one may be stop, the next one may be stop and parity, and finally break errors. Okay. And we can get a pretty good distribution of that. Down at the bottom, you'll see I'm kicking off my transaction operations, calling my send procedure. I'll talk about scoreboards in a little bit. Okay. Yeah, so again, our test is randomization plus code plus transaction calls. This sets us up to do constrained random. Okay. Now, the next thing, as soon as you start randomizing, you need functional coverage. We need to be able to track and make sure, did that thing I was looking to happen actually happen? Okay. And so we need a way to say, did I finish, right? And my view of test done is 100% to 100% code coverage. Okay. So we have two flavors of coverage. One is item coverage, looking at a single thing and perhaps binning it into ranges and such. Such as if you're looking at transfers, you might want to look individually at very small transfers because things break there, and then individually at big transfers, and then look at ranges in between. Okay, and that's what this is suggesting here with item coverage. Cross coverage, we need to correlate things between independent things. Okay, so the one we'll look at real quick in here is an ALU. We want to bin the different values that go, the different inputs that get selected into an ALU. Okay. Well, why not just code coverage? Well, there's a lot of good reasons for that. One, code coverage just tracks what's been executed. Okay? It doesn't do anything that's missing in the code. So correlating independent things, can't do that. Binning something that's not, can't do that. Besides the fact, code coverage is optimistic. Okay, it works great in software, right? But what about this HDL that runs on every single delta cycle? Well, it's recording code coverage on every single delta cycle, but not every single delta cycle is there at the end of the clock. It's really only the delta cycle, it's the last delta cycle that you run on before the clock. So code coverage does us something good in that if you don't have 100%, you certainly haven't done it. But if you have 100%, it doesn't tell us we're. Okay, so you need functional coverage on top of that. The way OSVVM does this is we bury in a protected type a data structure. We just got to build a table and count, did this happen, did this happen, did this happen. And we're just going to build ranges in there. So we have a number of different helper functions to do this. I'll talk more about them as we go through the example. The example, we have an ALU, very, very trivial ALU, an adder, okay, that can pull from 8 different registers and store to any one of those 8 different registers. And what I want to know is, did each possible selection on input get used with each possible selection on the other input? Okay, so, and this is about as easy as coverage gets. This is a Cartesian cross. Any language can do Cartesian crosses, okay? So we start out with a shared variable, okay, because that's what we're building our data structure in. But you don't need to know anything about shared variables beyond how to call them. And it's just like an OO language. It's the object name dot the method. Okay? Add cross. And then gen bin is something that splits ranges down into pieces somehow. Gen bin with just 2 parameters says break this range down into individual bins. So it's 0, 1, 2, 3. And then we're crossing it with another 0, 1, 2, 3, so we're going to get that 64-item cross product in there. Now we want to do our test. So we want to randomly pick things, and we're just going to use as uniform randomization. We'll call it twice, once to get each different source, and then we'll do our transaction. Okay? And then we'll collect our coverage. Now, I'm kind of cheating. I'm collecting the coverage right here in my code where I'm dispatching the transaction. To be able to do that, I have to validate that this can only do that. Otherwise, instead of doing this here, I've got to have an observer out at the inputs. And if you look at SystemVerilog formally, they break out a monitor model that watches this stuff for you. And yeah, you could do that, but I wanted to show a complete example here. Okay, and then when we're got everybody, we hit covered. Okay. So one of the takeaways here is functional coverage with OSVVM is just as simple and concise, interestingly enough, as SystemVerilog has built into the language. Okay, we'll come back to that in a minute, though. Now, the problem with uniform randomization are tests. How many of each of these do we need to see? Okay, 1, 2, 3, 5. That's a lot, right, for a test? You don't need to see thousands of them. Well, the problem with that is that convergence becomes an issue, right? So, because randomization repeats a lot. Okay, it's n times log n, which is roughly 5x too many. In the longer version, I could show you all the details, but I won't here. So what we have built into the coverage model is we have a method to randomize and take a random walk across the coverage model, because that's really what we want to have done in our test anyway. Okay, but we like the randomization because then the order is not deterministic, and if we run it a number of times, if we give it instead of just a simple add cross, if we give it a weight of say 10, we'll do everything 10 times. Okay, walking across different things. Okay, so the only thing we change is our randomization method. Okay, instead of using randint, we're pulling from the coverage library itself. We have a methodology there. We write functional coverage. We randomize using functional coverage. If we're looking at inputs, there's really no refinement to do. If we're looking at outputs, yeah, there's probably a lot of ad hoc code in there that we've got to add. But it gives us something that closes the coverage faster. Not saying that you don't need to run more vectors than that. Okay? Okay. Now, this is the slide I said I'd come back to. SystemVerilog does Cartesian crosses rarely nicely. Cool, good job. But it's all declarative. Now do something other than Cartesian crosses. Okay? And they've introduced a declarative method to subtract things, and it's insane. Okay? OSVVM, we build a data structure. We build it in sequential code. That means every single sequential construct you have in the language, you can use. Okay? So we can loop. We can use any construct. We can use generics to shape it. We can pass a coverage model as a generic. Okay, and all that it's been done. So, and actually passing it as a generic wasn't even my idea. It was just one of the guys was doing some cell phone tower processing and wanting to wander to space and wanted sometimes a small model and sometimes a big model, so he started passing it as a generic. And I'm like, cool. Okay. The next thing we have in OSVVM is things all about printing. Okay? We have log messages that we want to conditionally print some of the time, all of the time, none of the time. We have error messages that we always need to print. But we want some control over this stuff, and VHDL has a cert, but it doesn't give us any control except for at the simulation control command language, and it doesn't give us an accumulation of our errors. Okay. So OSVVM introduces transcripts. Transcripts is a file that we're going to log to. You can open it or not. If you don't open it, it dumps to standard out. But everything in OSVVM goes to the transcript file if you open it. And we also have a mirroring capability, so if you want it going to the file and your output, you can do both. Okay. We also support very simple printing of strings, or if you really, really like text.io, you can use text.io without a file name and dump to your transcript file. Okay. Anybody like text.io? I don't. Okay. Logs. Logs are really for debugging. We have log. All of ours support an ID or not. You have to allocate IDs. And they allow us to turn things on and off. We can turn logs on and off based on a ID. And basically when we set up this ID, I usually set it up so that it matches the instance label. So now I have some information printing out. If you don't have great instance labels, then you might want to include the model name itself too. Okay. So we have a number of different labels for different intentions. SystemVerilog went and did kind of levels. Okay, how many things work with just levels? Okay, I want things I can turn on. I want debug flags that I can turn on, but I want info flags I can turn on that are totally independent and are not level based at all. And when I'm done, I want a passed flag that indicates individual pieces of the test that have passed. I might not need this until my final report's done. I might need initially just to know that we passed overall. But then I might want for a report that each individual little aspect of the test passed, and I have a separate flag for that. Okay. And all of these can be turned on independently, and they can be turned on independently for different models with the ID fields. We have alerts. Alerts are for errors, error reporting. I use them mainly in the packages. And like an alert if for bounds checking. Totally opposite polarity by the way of assert. Asserts an alert if not. We have that too. So this is error failure warning. Okay. We have a stop count, so if you get 20 errors or 100 errors and you think you should be debugging by now, we can stop the simulation based on that just by setting the stop count. Okay. Affirmations are about self-checking. Okay, so affirmations combine alerts and logs. Remember, logs don't print unless you enable them. Alerts are automatically enabled and will only turn off if you turn them off. What else? So it works like alert. Reports the errors. You keep an error count behind the scenes. We keep the error count on a model-by-model basis, but it also accumulates against the top level. You don't have to use the model basis at all. You can just use the top level if you like. When the test is done, we can do report alerts. If you're just using the simple mode without the model IDs, you get a report that looks like this, either passed or failed. The reason I didn't collaborate with anybody else that had packages out there is I wanted this from the beginning, and they didn't have it. Okay, and they didn't have a path to get there. Thank you. I think I'll make that. Okay, so we can report all the errors by model. Find, that model shouldn't be part of the simulation anyway. I should have turned them off. Okay, so we shouldn't have been detecting anything. OSVVM also has scoreboards. Scoreboards are nothing more than a data structure to facilitate some forms of self-checking. We've had this since around 2006 is when it came into play. It's got a FIFO inside, but we also have methods to help checking. We could handle out-of-order execution. We can handle drop values. It's a generic scoreboard. You set it up so that you define your types and such in other packages, and you map it. Okay. So the use model, we define a shared variable, the scoreboard type. We push things, we send our transaction, and then we get things and we check our transaction. Okay. We'll also do memory modeling. Okay. So the problem with memories is you can wipe out your whole storage in your workstation just by implementing it with standard logic vector and as a signal. Okay. So what we do behind the scenes in memory package is an array of pointers that point to integer locations that we use as a storage location. We allocate, I think by default right now it's 1,000 at a time. Okay. And this makes memory modeling more efficient. How much more efficient? I had a client that was using their own memory model. I think it was from Altera. Their simulation was taking 24 hours. Swapped it out with this. Actually, the precursor to this, it took an hour. Okay, so that's huge. It's very simple to use. It's another protected type. Again, you don't have to understand that. You just have to declare a shared variable. We have to initialize it. We dynamically size it, okay, because we didn't have package generics when this evolved. So eventually I'm going to go back, and the next language revision introduces generics on protected types. It's going to become that eventually. Okay, so that we won't need the init. Then you can do a separate RAM and a separate write, a separate read. I just used this to swap out Actel's memory model on a project, not for runtime, but because they wanted to check their EDAX, and they didn't have any way to inject an error. With protected types, you can access these things with a VHDL feature called external names. That's nothing more than a hierarchical reference. We have a number of synchronization primitives in the library. The top ones used in our test control and dispatching sequencing tests. The bottom ones are a couple of the ones we use for model interaction the scenes. Okay. We have libraries. Our AXI Lite models, master's beta, slave is alpha. Slave, what's wrong with it right now is it's got the wrong set of generics on it. They need to be swapped out and updated. AXI stream models, we've got alphas on all that. We've got UARTs that are internal. But what we're really looking to do long term is firm up. Somebody said this the other day about UVM. We need to firm up our modeling style, and then we hope to recruit perhaps some master students or something to put some additional models in place in the library. We're supported by a community on osvvm.org. We also have our whole sites on GitHub. I blog about it on our old website sometimes too. I blog about it on LinkedIn quite a bit. Wrapping up then, OSVVM provides you all the pieces of your verification puzzle. Got a lot of them by picking fights with SystemVerilog people, and they say, oh no, you can't do this, so that was my next project. Figuring out what to do next. OSVVM is powerful, it's concise. We actually, again, do more than SystemVerilog does, more capability with cross coverage. We also do deep introspection into the coverage and do the randomization, which is something that they don't do at all. It's simple. We want readable tests. We want readable tests in one file, not lots of files. Okay, you look at SystemVerilog, your tests are everywhere. We run in any VHDL environment, and hey, it's just writing code. And VHDL is adequate for doing that. Okay. We support mixed approaches, mixing directed, as well as constrained random, and our intelligent testbench methodology. By the way, our intelligent testbench methodology is like a lightweight version of part of the aspect of what they're trying to solve with portable stimulus. Okay, their next generation standard. Okay. All right.
Thank you very much. Questions?
They're all ready for lunch.
They're waiting for lunch. No question.
One back there. I didn't bring my big fly swatter.
About a year ago, I did a course on UVM because the company I work for does SystemVerilog. The impression I got was the fact that there was an awful lot of just stuff that was under the hood with UVM, and that makes me very untrustworthy. For me, trust is an important thing, and I just didn't trust that stuff. So it's nice to see the fact that my original language, VHDL, has got this.
Cool. How many people do VHDL, at least at the RTL level? Anybody using OSVVM now? All right.
One. So if there are no more questions, let's thank the speaker again.